Welcome. Coping with information loss and the use of exhilarating sources of data. This is the fifth in a series of lectures and workshops that we've been having on how to deal with unplanned disruptions in clinical trials. This series is part of a series that belongs to an Ingram Olkin forum. These forums were set up to honor Ingram Olkin after his passing, and the forums as a group deal with a current societal issue that maybe doesn't have enough attention from the statistical community. Now, when we started this series, that was true of the topic, and of course, there's been a lot happening since. But the series as a whole tried to look at issues that for which statisticians and practitioners need to get together and to develop or further or stimulate the field. And it's not your typical lectures in that this is not intended to be a one-way street with the speakers just speaking to the rest of you. The intention is through the discussion groups and through meetings that we organize later on for those that are interested to develop a working group that will actually try to help these methods develop and or be implemented more completely and satisfactorily in practice. So we hope some new collaborations come out of this, and we look forward to meeting everybody more individually in the discussion groups. So in this particular series, we started out with 2 sessions where we had the perspectives from statistical leaders and government agencies. And those were in a lecture format to give us an overview. Of course, we didn't really expect to be dealing with COVID as we are at this time, but here we are. And these overview lectures as to what were the problems that were being seen on the ground then are followed up by specific methodologically oriented topics that we thought people with expertise in these areas could perhaps, contribute to how this particular methodology could help with unplanned clinical trial disruptions. So we've had a session on estimands and missing data. We've had a session on randomization tests. And after this, we have a session pretty well organized now on Bayes and frequentist approaches. And we'll follow that with some work on group sequential designs and sample size re-estimation, sort of depending on how the estimands issue working group puts together what they are doing. So for today, here's the session. Here, you've already seen the overview of the session today. I'm going to turn this over to Chris Jennison to moderate the speakers and to say a little bit more about the breakout discussions and what we'll be looking for to happen there. So with that, I will turn it over to Chris, and I'm sorry about fumbling the technical details here.
Okay, so thank you very much, Nancy. It's a pleasure to welcome everyone. I look at the names and think it's great. A lot of old friends here, and also some new names, at least to me. And we're looking forward to some enjoyable exchanges. Of course, the setting is a fairly tragic one. I mean, it's March the 23rd. In the UK, it's a year to the day since we went into sort of the first phase of lockdown, and I'm sure it's something similar for everyone else. And we didn't really expect to be like this still at this time of this year. So there have been, as well as all the interesting developments in COVID treatments, a lot of trials that have been disrupted quite seriously, whether they've even started again since the initial disruption, will be very variable. So today's topic, how to make up for that by finding other sources of information that were not those initially planned, is very pertinent. And we've got 3 speakers to look forward to talk about this. Now, the aim, as Nancy was saying, the aim of the whole forum is to identify questions. So we want questions, if you like, rather than answers. The speakers will have best part of half an hour. There can be a bit of time at the end of those talks for some questions, but they should be very much, helping to clarify understanding questions. You can also, if you're along the way, put things into the chat if you want to raise a question that can be passed on at the end to the speaker. And then when we go to the breakout rooms, our job is to really work out what are the challenges. We'll have seen some approaches, we'll have seen some possible gaps in the way they would work or new questions that they've raised. Can we identify those more clearly with a view to setting up research groups who can then work together to try and meet those challenges? And we have our moderators, Lisa and Sarah, to lead us through that process. So I think without any further ado, I should introduce our first speaker. And this is Nigel Stallard. Nigel, who has degrees from Cambridge and then Reading, and has been at Warwick University since 2005, professor of medical statistics there. So welcome, Nigel. And Nigel is going to talk to us about using short-term endpoint data in interrupted clinical trials.
Thank you. Let me try and share my screen.
Email this morning.
Well, if that works.
Yeah, click on this email to verify.
Okay, I hope you can see my slides now. So thank you, Chris, for the introduction, and thank you.
You're getting old.
Somebody needs to mute all of the organising.
Yeah. Can I interrupt Nigel for a second? Could everyone else who's not Nigel go to mute, please? Okay, off you go, Nigel.
Thanks, Chris. So thanks to the organisers for inviting me to take part in this session, which looks like it should be a really good meeting. So I want to just start by, I suppose, acknowledging the huge effort that has gone into clinical research over the last year. There's a database where you can look up all of the trials that are going on in COVID-19, and that will show you that there are over 2,500 trials which were started last year, with 650 of them in April alone, which I think is truly phenomenal. And obviously that's led to enormous advances, effective vaccines and effective treatments. And the prognosis looks very different, I think, to this time last year. But alongside those 2,500 new trials in COVID-19, and this is a number that came from Sarah Zohar, I think, there are around 5,000 trials which were ongoing in other disease areas when the pandemic hit. And of course, many of those trials were disrupted, and they were disrupted for all sorts of reasons. Non-essential procedures were cancelled. There were restrictions on whether people could even attend for face-to-face assessments. And even when they could attend, perhaps they decided that they didn't wish to, or people were too ill to do so. And so we know that trials have been disrupted. Now, many of those trials will start again and will continue. But of course, for some of trials, that won't be possible. And so it's really in that context that we're thinking today. And trials will be impacted in different ways. So here's a sort of picture of perhaps what we might have sort of set out with our trial running through time. We recruit some patients, we follow them up for a period, And then at the end of that follow-up period, we observe the outcome that we're interested in, which is marked by the sort of solid dot at the end of each of these lines. And by the time we get up to the end here, we've got all our data. That was what we were hoping. Of course, things don't always go as we hope. And at some point, the pandemic hit. And so the trial is interrupted, and we don't get to perhaps recruit all the patients, and we don't get to see all of the outcomes. The trial can be disrupted in different ways, of course. So the picture here shows a trial which perhaps is disrupted near the end. Here's one which is disrupted right at the beginning, so that there's very little data. Here's another one where we have quite a long follow-up period, where perhaps we have recruited all of the patients already, or most of the patients, but we have rather little follow-up data because most of the patients are in the follow-up phase. And it's this setting which I'm particularly interested in today. And in particular, the setting where we might have some early endpoint data. So it's very common to not only measure an endpoint at the end of the follow-up period, but in a trial with long follow-up, to also record things earlier on. So it may be that for many, or perhaps even all of the patients, although we don't have the final data, we do have some early data on an early endpoint. And the question really then is, well, what can we do with that data? How can we use that data to help us interpret and learn from what we do have in the final follow-up data on the much smaller number of patients, because our trial has been disrupted. And one thing that we might do, which is not really the focus of what I want to be talking about today, is to think about changing the endpoint. So we could actually say, well, we're not going to see the final endpoint that we wanted to see. We are going to get data on this earlier endpoint. Why don't we just use that instead? And so all of our inference will then be based on that different endpoint. And we might want to think about, well, when can we do that? And I think really the criteria here are actually quite similar to the sort of criteria we might think about when we're choosing a surrogate. And I guess the most important one is really about the question of clinical plausibility. You know, why did we choose the endpoint which we actually was initially our primary endpoint? Why did we feel that was better than this early endpoint? Is the early endpoint going to be reliable? Is it going to give us the information that we want? Is it really the thing that we're interested in? We can also ask sort of statistical questions. You know, when is it that statistically it might be appropriate to use this early endpoint rather than the primary one? And to help sort of think about those, I've got these sort of two pictures here where we've got kind of two groups, which we can imagine being a treated group in red and a control group in blue. And for each of those groups, we imagine the primary outcome and the early outcome drawn onto the sort of scatter plot here. Now, an obvious thing that we might want to do if we want to use an early outcome in place of the primary outcome is to say, well, we want the outcomes to be correlated. The outcomes are correlated in both of the cases. You can see that the points sort of, you know, are kind of lying in ellipses, if you like, rather than in circles, so that a large value on the primary outcome tends to be associated with a larger outcome on the early outcome. But actually the pictures are quite different, because what's different here is that they've got different treatment effects on the two outcomes. So the picture on the left shows that there's a treatment difference between the means of the groups, both on the primary outcome and on the early outcome, whereas the picture on the right shows there's a difference on the primary outcome, but really there's no difference on the early outcome. And really to be able to use the early outcome in place of the primary one, obviously we need to be in the situation on the left, where there's a treatment difference. If there's no treatment difference on the early outcome, then obviously that's not going to give us the information we want. So we actually want this relationship between the means, if you like, we want the means to be correlated, as well as the correlation within the groups to be able to switch the outcome in this way. And obviously whether we'll have, what power we'll have will depend on the size of the treatment effect, relative to the variance on the new outcome that we choose to use. So that's something that we might do, but as I say, that's not really what I want to talk about today. What I really want to focus on is a situation when we don't want to change the endpoint that we're interested in. We're still interested in the primary endpoint, but somehow because we have this extra information on the earlier outcome, because we've got more people who we've observed this for, can we somehow use that information to help us in our inference on the primary endpoint? And the answer is that yes, we can. And although the situation that we find ourselves in is an unprecedented one, the sort of data that we've got, the sort of data structure where we've got primary endpoint data on some people and early endpoint data on a larger group of people, is not a completely unprecedented one, because it's a situation which arises during the interim analyses of a trial which is a sequential trial. And so to just show that, here's a picture which is just lifted from a paper by Van Lanker, showing essentially exactly the same picture that I had a couple of slides ago, except there's no pandemic in this picture. It's just that the incomplete data are being analyzed at an interim analysis. And so the sort of methods that are referred to in the papers here will perhaps give us something which we can use in this new situation. Of course, it's not exactly the same, because if we're doing an interim analysis, then we will go on to observe the final data. So we will go on to follow up these patients and see the final outcome, the primary outcome for them, whereas in our situation, we won't. But nevertheless, we can perhaps use this method, and really that's what I'm going to be talking about in this talk. So the idea that we are going to do is sort of set out at the bottom of the slide here. We're going to sort of specify a model, a joint model for the early and final endpoints that we're observing. We can then obtain a likelihood, and then we can obtain maximum likelihood estimates for the final endpoint parameters. So as I say, we're still focusing on that final primary endpoint. It's not that we're somehow switching endpoint, or that we're kind of forming a new composite endpoint, but nevertheless, we can use these early endpoint data to help us learn about the primary outcome. And I'm really going to just run through some examples to show how that might work. And the first one is perhaps the simplest example I could think of. I'm going to focus on just a single group. So we've got no treatment effects going on here. If we can gain something in a single group, of course, we can then do that in two groups and then look at treatment effects. And I'm going to be thinking just of the binary outcome of death by some time t. And let's first of all kind of just focus on that alone, and then we can think about the early endpoint in addition in a second. So this is a rather dull slide. We've got n individuals that we've observed, and we've seen that d of those have died by time t, and the remaining n minus d have not died. And we want to estimate p, the probability of death. And not surprisingly, we just estimate that by looking at the proportion of those who've died. So our estimate is just going to be d over n, which we know to be unbiased, and we know to have a variance p1 minus p over n. What now happens if we think about the early endpoint data as well? So suppose in addition to observing deaths at time t, We also observed whether the patients were alive or not at an earlier time, T1. And for the moment, I'm not thinking about additional patients. I'm only going to think about these N patients and see what happens there. And then in a moment, I'm going to think about what happens when we've got some additional patients where we only observe this earlier event. So now, in addition to knowing that we've got D patients who die by time T, we also know that E of those had died by the earlier time T1. So at the early time, out of our N patients, we'd seen E of them died and N minus E were still alive. And so the deaths by time T obviously include all of these E, people don't come back to life. So we've got E who died by time T1, and then we've got the remaining D minus E who've died in between time T1 and time T. So these N minus E and D minus E of them go and die here, and the remaining N minus D are still alive at the end. And now we've got an additional parameter, which is I'm going to call P1, which is just the probability of death by time T1. But we're still interested in estimating P, the probability of death by time T. So we can write down the likelihood. There are three things we can observe. We observe E people who die by time T1. We observe D minus E people who were alive at time T1 but die by time T, and the probability of that is just P minus P1. And then we observe N minus D people who are still alive at the end, and the probability of that is 1 minus P. So this is our likelihood. We can maximize our likelihood, and we can get a maximum likelihood estimate for P1 and substitute that back in. And so we get the maximum likelihood estimate for P, and in fact, that's just still D over N. So if all we've done is seen whether they died by time T1 or not, then we don't get any more information on the death rate or the probability of death by time T, other than by seeing how many people are still alive at time T. That's not surprising. But we can write this estimate in a different way, because we can think about the probability of death by time T as being the sum of the probability of death by time T1 plus the product of the probability of being alive at time T1 multiplied by the probability of death at time T, given that you're alive at time T1. And then you can estimate each one of those parts from the data that we've got up here. So the probability of death at time T1 is just going to be E over N. The probability of being alive at time T1 is going to be N minus E over N, so that's the bit here. And the probability of dying by time T, given that you're alive at time T1, is just D minus E divided by N minus E. So that's the term here. And all of this just cancels back, and you get back to exactly the same estimate here. But that perhaps starts to give us some insight into how we could use additional data if we have other patients who we only observe by time at time T1. So let's think about that now. So I've added those patients into the slide here in red. So in addition to the patients we've been talking about so far, suppose we now have a total of M patients who we only observe at time T1. So we don't know what their outcome is at time T, but we do know that of those M patients, F of them die by time T1, and M minus F of them survive to time T1. So the likelihood now we can write down in a similar way. So now we've got some patients who've died by time T1. There's E of them here and F more of them over here. We've got some patients who died between time T1 and T. We've got D minus E of those.
No confidentiality issues, genau.
And we've got some
Und der Vorteil, kann dann ja eventuell uns
sorry, could I ask you to mute yourself, please?
auch sich dann draufstellen
I think someone is talking.
Mute yourself, please.
Thanks. And we've got some patients now who we only know have survived up to time T1. So the probability of that is just 1 minus P1. And it turns out that the maximum likelihood estimate of P is given by exactly the same expression as we had before when we just estimate things in the obvious way. So now we can estimate the probability of death by time T1 as being E plus F divided by M plus N. And the probability of being alive at time T1 is just M minus E plus M minus F divided by M plus N. And the only information we've got on on the probability of death at time T, given that you're alive at time T1, comes from patients where we've observed both of those things. So that just comes from these patients here. So that's just going to be a D minus E over M minus E, exactly the same. So we now get a new expression here, which is not the same as we had before, because it's included this additional information. And note that that's not the same as just including these additional patients in a very naive way and just thinking, well, we've just seen an extra F deaths, we'll just kind of add those in somehow, because this is allowing for the fact that we've got this kind of more complicated likelihood. So this is our estimate. It's still unbiased, but its variance is not the same as it was before. And in particular, the variance is smaller than it was before. So the variance before was just P times 1 minus P over N. It's now that multiplied by 1 minus rho squared M over N plus M, where rho is just the correlation between E and D. And in fact, rho squared is then just the odds ratio of P1, 1 minus P over 1 minus P1 times P. And so you can see that by using these additional patients' data, we've got an unbiased estimate, but that's got a smaller variance because we're gaining information from these early endpoint data. Perhaps that's not that surprising. You know, if we know patients have died by time T1, then of course we do know something. We know they're still going to be dead by time T. So we can, if you like, look forward into the future and know what's going to happen. What about other sorts of endpoints? Can we do something similar there? Well, it turns out that we can. In particular, for example, let's think about a single group of normal data where we now have our primary endpoint, which I'll call Y, but we have some early endpoint, X, where I'm going to assume that X and Y have a multivariate or bivariate normal distribution. And the thing we're interested in here is mu, the mean of the primary endpoint Y. We're not really interested in mu X, the mean of the early endpoint. So we've got N observations again, where we observe both X and Y. And then we have an additional M observations where we just observe X. So we don't observe the primary endpoint. And once again, we want to try to use those additional early endpoint observations to gain some information to help us learn about mu. So here's a sort of picture. We've got, I've got some kind of observations here on the primary endpoint, which I've just shown by these sort of tick marks. I've shown a sort of fitted normal distribution to them. This is the mean, and this is just the standard 95% confidence interval for the mean that we would work out from those observations. If we have early endpoint data for those patients as well, then we can sort of draw them on the scatter plot here. And perhaps we can start to see that in this case, maybe we believe there's some positive correlation here. It looks like typically the larger values here are associated on the whole with larger values here and vice versa. So it looks like we've got a sort of early endpoint here, which is correlated with the primary outcome that we're interested in. And here's the mean that we observe for those patients on the early outcome. Suppose we now have some additional patients for whom we only see the early outcome. So once again, I've shown them in red. So here are some additional patients, and I fitted a normal to them too. And you can see that the mean for these patients is slightly larger than the mean for the patients where we've got the primary outcome data. So it looks like maybe we were, if you like, unlucky and happened to choose a bunch of patients here who had a slightly smaller mean on the early outcome than the whole population that they were being drawn from. And if we believe that, and if we believe that the early outcome and the primary outcome are correlated, then maybe we also believe that this is an underestimate of the primary outcome mean. So maybe we somehow want to shift our estimate up to reflect the fact that it looks like the patients we've happened to choose have rather smaller than sort of the whole population outcomes on the early outcome. And that really kind of is the idea of how we might change our estimate here. Once again, you can sort of write down the joint likelihood, and you get a sort of bivariate normal part from patients where you've seen both outcomes, and a normal part for just the early outcome for those where that's all you've seen. And you can obtain maximum likelihood estimate for mu using a method which Engel and Velstra call double regression. And what essentially you do is you do something which actually is rather similar to what we did in the binary case. You use the data where you've got kind of both outcomes to learn about the relationship between them, and then you sort of moderate that using the data where you only seen the early outcome. So you fit a regression model which relates the primary outcome to the early outcome using the n patient data that has both of those. You get estimates alpha hat and beta hat for that regression. And then you take the mean for all of the patients, all n plus m of them, where you've seen the early outcome data, and you form a new estimate, mu, which is just alpha hat plus beta hat times that mean. I'll show a picture once again to illustrate that. So here's exactly the data that we had a moment ago. We can fit a regression line based on those observations. And we know that the regression line has the property that the mean of the x's for these n patients, if you take that and multiply it by beta hat and add alpha hat, you just get to the mean of the y's. But what we know is that we've got some more additional data here. We've got some additional early endpoint data. So the mean of our whole sample of early endpoint data is given by this red dotted line here. And so we shift the mean up to get a new estimate of our response on the primary outcome, reflecting this additional information. And if I just go back, then this has very similar properties to what we saw for the one in the binary case. Once again, it's an unbiased estimate. And once again, the variance is smaller than that we would get from just using the primary endpoint data for our n observations where we've seen that. That would, of course, just be sigma squared over n. And once again, we've multiplied it by something which actually looks exactly the same as it did before, where now our rho is the correlation again between the early and primary endpoints now in the bivariate normal setting. So just some sort of notes on that, and I'm aware I'm nearly out of time. we can think about the information in terms of the variance reduction as being rather like a sort of effective sample size, which is then given by this expression here. And you can see that this lies between n and m plus n, so that it's going to be n when rho is equal to 0. So if you've got uncorrelated endpoints, then you don't gain anything from looking at them. But if rho is going towards 1, then actually you gain like all of the information that you would have seen had you seen primary endpoints on all of those n plus m patients. Of course, what that means is we can't get more information than we would have done from that total sample size. So if we haven't, and typically, of course, rho won't be 1, so we will end up with less information even if we use it in this way. If I can perhaps have a couple more minutes, I think Chris is nodding,
Okay.
then I'll perhaps just sort of talk a little bit about another way of looking at where the estimates we've got come from. And that's thinking about this as a sort of missing data problem. So what we've got is we've got the early data from these M patients, but of course we don't know what their final endpoint will be like. And so we can perhaps try to, if you like, sort of imagine what that might be. So of course, we know that these F patients here are going to still be dead at time t. So we know that those will die. But what about these patients here? These patients are currently alive. So how many of these do we expect to be alive, and how many do we expect to be dead by the time we get to time t? Well, our best estimate of that, of course, comes from looking at these patients and seeing how many of these went on to die and how many of them remained alive. So we can get an expected number based on that, like this. So we can just take this m minus f and multiply it by the proportion of these patients who die is just d minus e over m minus e, and then the remainder will be alive. And if we then just took this number and divided it by m to get a new estimate, sorry, m plus n, to get a new estimate, then actually that's exactly the same estimate as we had before. So the estimate we've got is identical to what we would get if we just looked at the expected number of deaths based on the data that we've seen. And exactly the same thing happens in the normal case. If we just replaced each of these observations here by its sort of fitted value on the fitted line, and then added those observations here, then we get exactly the same estimate here as we had before from the double regression. So there's quite an easy way, if you like, to reconstruct the estimate. Of course, reconstructing the variance is rather more difficult here. Though actually, I did have a quick go at just thinking about this as a missing data problem and just doing some sort of multiple imputation and using sort of Rubin's rules, and actually got very, very close answers to the variance which we get from the double regression, which I think perhaps might be an interesting thing to think about. So I suppose really that leads on to, in some sense, the point of today is to sort of think about where this might go and what perhaps some of the open questions are. I hope other people will have open questions too. I think there are some interesting questions about extending this to other types of data, in particular, I suppose, sort of time to event data. And I suppose there's some interesting things thinking about the early deaths and thinking, well, actually, you can imagine early deaths observed at lots and lots of times, and that's a bit like the time of death. And how can you then use that, and is that related? And what happens if you have a time to event outcome and you observe something else early on? As I say, links to missing data are interesting, and links to sort of questions of regulatory issues are interesting too, and no doubt there'll be other questions as well. Thank you.
Okay. Thank you very much, Nigel. And in the interest of time, I mean, I think it was very clear, and I'd be surprised if there are too many questions of understanding, but if anyone has a burning question to try and understand something that they didn't quite get there, please go ahead and ask. And if not, we'll move on. There was a comment in the chat noting the relation between what you're doing there, Nigel, and Kaplan-Meier estimates. And I think in the survival data context, that's something to follow up.
Yeah, exactly. And I think, as you say, that's an interesting point. And I think.
But I think we'll take this forward, and I think the questions we can look at in the discussions are to do with the context of this and the assumptions and maybe generalizations. So thank you very much, Nigel. And now we're going to move on to our second speaker. And this is Mark van der Merlebrugge. And Mark was educated in Paris, Munster, Magdeburg, and Manchester for his different degrees. And he's now at Novartis in Basel as the global group head in their analytics department. So Mark, thank you very much for joining us today. And we're looking forward to hearing you talk on mitigating force majeure trial disruptions by leveraging external data. Over to you, Mark.
Thank you, Chris. Can you hear me? Can you see my screen?
Yes, you could make, oh, there we go. Yeah, full screen now. That's brilliant.
Okay, excellent. So thanks a lot for inviting me to speak here. I will speak about force majeure, so higher force trial disruptions and how to mitigate those potentially using external data in contrast to Nigel's topic. And I have a case study that focuses on pooling as the approach. I'd like to give some credit, especially to Eva Hua, who is the lead statistician on this project in my team, and then also a number of collaborators and consultants, Frank Bretz, Paul Gallo, Reinhold Janocha, Thomas Severin, Jia Wei, and Dong Shi. So what do we mean by force majeure trial disruptions? I guess by now we should have a good understanding. This is, let's say, we have a trial here, investigational drug versus control, and at some point, something happens and the trial cannot continue. And I get less information than I thought I would get. And so the question is, well, what should I do? And I'd like to start with a few quotes from a special issue from Stats in Biopharmaceutical Research. 3 different papers in the same issue. First one here is from Rob Hemmings. What he says is supportive approaches might look to integrate data from external sources to augment the control arm or pool trial data with results from previous studies. The second example is from Muna Akacha and colleagues from Novartis. Other approaches to compensate for lost information can be considered as well, such as leveraging data on short-term endpoints that are correlated with a primary response, or to integrate data from external sources to augment the control arm or pool trial data, with reference to the paper from Rob Hemmings I shared in the previous slide. And lastly, another paper, again from the same special issue, in this case from Dan Meyer. This is a cross-company, cross-industry collaboration position paper. What these people say is, given the extraordinary circumstances, we advocate more flexibility to consider methods for quantifying evidence across multiple trials and sources, including use of historical control arm data and real-world data. So all these papers point in the direction that we can use external data sources, external information of various types. And of course, in these papers, we don't have a lot of details, but I would like to open some thoughts on the details in this particular talk. So when such a thing happens, my trial is struck, I don't get enough information. The first question I might want to ask myself is, how much power do I lose? And in a special case, at least, this is fairly simple to calculate, and this has been published by Kunz and Muna Akacha. So say we have a trial with level alpha test, power 1 minus beta, and we have a normally distributed test statistic. And we have a fraction P of the targeted information available. This may be a fraction P of the sample size or of the events I have thought of. It is smaller than 1. That's the point. In that case, the power is simply given by this particular formula. It depends on alpha, beta, and that fraction. And it is meant to be the power at the same alternative hypothesis where I powered the original trial design. And now I can plot this for alpha equal 0.025, 1 minus beta equal 90%. And this is how it looks like. By the way, I hope that you do not see the ribbon of participants that hides the plot in what I see. I hope that you see the complete plot. So you can see the power is at 90% when I have the full sample size, but when I go down to 80, 60%, say even 50, 40%, I lose substantial power. Chris is nodding. I suppose you see the full plot. Good, excellent.
Yep.
Thanks a lot. So that might be the first question I want to ask myself. How much power have I lost? The second question is, well, how should I compensate for this loss? And we have heard from Nigel, well, I might want to leverage short-term endpoint data. In this and the next talk, we might want to look into external information. And there may be other ideas. That may be a topic for the discussion after our talks. You know, maybe there's more concepts how I can compensate for lost power. Now, if I settle on using external trial data, then the next question is, what external data sources are there? Okay. Historical data is something referenced in those papers I quoted earlier. Clearly, completed studies from the same development program are a potential source. And also other studies from other programs or even other sponsors. Typical examples include the use of control arm data from the same indication from other sponsors. Usually, when we go outside of the program we are developing, we have more data, but sometimes this data can be older. Sometimes the trials may be different from ours, so there's more things to consider here. And last but not least, we could look into real-world data as a possible source, and the talk after mine will go into this direction. Now, besides historical data, we can look into concurrent data. And this is the case in the case study that I will focus on a little later in this talk. We could consider parallel studies from the same development program, such as a replicate phase 3 study, or if I have, say, a placebo-controlled phase 3, I might even have a head-to-head, which is running in parallel, and that could give additional information. And also here, I might have concurrent real-world data. So all these are possible sources. Now, the next question is, what should I consider when I do leverage these external sources? The first point I would like to highlight is time trends. And this has been recognized already a while ago by Nicholas et al. And there have been updates of this work ever since. This is a famous example of annualized relapse rates in relapsing remitting multiple sclerosis, where you can see the relapse rates from the placebo arms of clinical trials, they go down over time, massively. So for whatever reason this might be, you know, improvements in standard of care, whatever it might be, this is something we have to take into account when we want to use historical data to complement loss of information in a current trial. And then there's a number of other elements to take into account, and I will just list them here quickly. There may be differences in the population. There may be differences in the way the endpoint is defined, even if it carries the same name, sometimes it's defined differently. Treatment regimens may differ. the trials may be run in different regions compared to the one that I'm looking at. Co-medications might be allowed or not allowed in different data sources, and a whole host of other protocol aspects, especially also when we think about real-world evidence as a information source. There may be a lot of differences in terms of what is happening in these types of, say, registries or trials compared to the one I would like to complement with more information. So some of these aspects may also play into the discussion later, but I want to move on to the next question. That is, how can I then bring this data together? Imagine I have chosen my data source. What kind of techniques could I use to incorporate this information into my trial? The simplest one might be pooling, and this is the one I want to focus later on. Then, of course, I might do some kind of regression. I might want to adjust for covariates if there's differences in the population, for example. I might want to do a meta-analysis, especially if I don't have individual patient data in what I use for complementing trials information. In particular here, the meta-analytic predictive approach has been used a lot, and I'll have one slide on that later too. I might want to use propensity score methods, again, to account for differences, and the talk after mine will focus on this. Or I might even go to some more mechanistic types of approaches like modeling and simulation, even physiologically based PK or quantitative systems pharmacology. And there are papers out there, I quote one here, which have proposed to do exactly that, basically creating virtual patient populations as complementary evidence. In this particular talk, I will focus a little bit on this meta-analysis approach, and my case study will then focus much more on the pooling approach. So let me start with meta-analysis. This is an approach published about 10, 11 years ago by Bert Neuenschwander. It's typically used for leveraging historical information, and it accounts for between trial variability by discounting the information. So let's say if I have a lot of control arms from historical trials, maybe with 500 patients, I will not count this information as equivalent to 500 patients inside my trial. I will discount it to account for any type of between trial variability. This approach has been used a lot. It has also been accepted in certain situations by health authorities. And just to have a glimpse of the method here, the idea is that my historical trials, they all follow some kind of distribution, say the effect on, imagine placebo arm data. This follows some kind of means, θ1 to θk. And my placebo arm in the current study that I want to complement with this historical information as a mean effect of θ star. And the idea here is that all these θs, the historical ones, as well as mine in the current trial, they are all derived from the same meta distribution, if you will. They are all instances of the same meta distribution of placebo data. And by that mean, I can incorporate this historical information and at the same time discount it for between trial variation. I'm not going to say much more about this one here. Just quote two examples. This is one that I was involved in just 2 years after the Bert Neuenschwander paper. You can see these historical θs from placebo arms of 4 different historical trials. They give rise to a predicted distribution for control data in my trial. So this would be virtual data. And you can see that this θ star prediction here has a much wider confidence interval than those source data, θ1 to θ4, which means I have discounted this information and I I do account for between trial variability. Another more recent example is from multiple sclerosis, where the same approach was used for pediatric extrapolation. And this was part of FDA's Complex Innovative Designs program. Same principle here. You can see 4 different trials as source data, data from adults and children, and all this gives rise to a prediction for a newly planned trial in children. This is just to say that these approaches have been published, they have been accepted by authorities, and they are fairly established. But now let me move on to my case study, which is not a meta-analysis, but pooling approach. And to start off, I would like to forget about the pandemic, as difficult as this may be, and mention that pooling approaches have been discussed even without trial disruptions. And this is from a paper by Jeff Matza here. So imagine there's 2 pivotal trials, each at alpha equal 0.025, type 1 error. It is well known that one large trial at alpha equals 0.000625 provides the same false positive protection as wanting to have both individual trials significant. Okay. Now imagine further that both trials have been powered at 90%. What is the chance that the pool of both trials will then succeed? Well, it is 91%, and this is bigger than the program power of the individual trial approach. So let me take this once more. 2 pivotal trials, each powered at, each at type 1 error 0.025. The same false positive protection is achieved by one large trial at alpha 0.000625. The 2 individual trials, if they're powered at 90%, then the chance to have both significant is just 0.9 square, which is 81%. But a pooled analysis of these trials at this smaller type 1 error has a much greater power. How is that possible? Well, this is what Jeff Matza and colleagues have published. We can look at this situation graphically. Say I plot the p-value from the first trial versus the p-value from the second trial in this diagram here. And I picture the rejection regions of these trials here. If I want both trials to be significant, this means that the p-value from trial 1 needs to be below 0.025, and the p-value from trial 2 needs to be below 0.025 as well. So I'm looking at this square B and D. This is my rejection region if I want both trials to be significant. However, if I pool the trials, my rejection region is actually A, B, and C. And I have designed this such that the probability of these 2 events is the same under the null. So landing in the region ABC is equally likely with landing in the region B and D, the 2 trials approach, under the null. The point, however, is that under alternative hypothesis, this becomes an inequality. And that's why I have greater power with the pooled approach compared to the 2 individual trials approach. This has been published regardless of any kind of trial interruption. Okay, but now the question is, we do have a trial interruption. Perhaps we can leverage this idea now. Say I have 2 trials, but they are curtailed by some kind of major event, and I only have 85% of the planned overall sample size. If I now do a pooled analysis at this smaller alpha, 0.000625, I have power 84% by this mechanism I just mentioned. And you will note that this 84%, of course, is smaller than the 91 with full trials, but it is larger than the 81, which I have with 2 separate fully recruited trials. So this could be an idea of mitigating information loss. In addition, this 0.000625 is not set in stone, right? Maybe for secondary endpoints, maybe in some situations, this can even be relaxed, but I'm not going to discuss this here. One consideration, though, is poolability, right? If I pool the trials, I need to make sure that I can actually do that sensibly. So they need to have the same or very similar protocols. They need to have comparable populations. Endpoints have to be designed, defined the same way, etc. And in addition to these design poolabilities, I can also build in statistical poolability checks. And I'm not going to say anything on this slide, but I have something on this a little later. So trials have to be poolable in order to pool them. Now let's look at the case study. This was kind of the preamble, the idea of pooling trials, initially published without trial disruptions, but now potentially used as a mechanism in case of trial disruptions. The case study here is as follows. Imagine I have 2 identical pivotal trials. Each of them uses a high dose, a low dose, an active control, and placebo. I'm testing various hypotheses in each of the trials. And I will use this type of nomenclature here for my null hypothesis that I want to test. So this is hypothesis for the primary endpoint, testing the high dose versus placebo, okay? And you can imagine secondary endpoints. I have number 2 to 5. The low dose has a little L here. And if I test against the active control, I will put a C in the last digit. This is the way I describe my hypothesis. And these trials, they're actual trials, they're currently running. They are sufficiently powered for the primary endpoint for both high and low dose versus active control. Okay, so this is important. They're not only powered against placebo, they're also sufficiently powered against active control with the planned sample size. Here's the pivotal testing strategy. And I need to explain this a little bit for those people not familiar with these types of graphs. This displays how I allocate my type 1 error level for all the different hypotheses. So let's start at the top here. I have 2 doses, low dose and high dose, in my trial. And by the way, this is the diagram for one trial. I have exactly the same separately for the other trial. So what I do here is I have the top node on the left is my hypothesis of the primary endpoint, low dose versus placebo. And on the top right, I have my null hypothesis for the primary endpoint, high dose versus placebo. And this little 1/2, this half here, left and right, means that I allocate half the alpha I have to each of the doses. So I start testing the low dose against placebo on the primary endpoint with half alpha, and the same for the high dose with the other half alpha. And now this arrow that moves from the first dot to the second here means that if I achieve significance on the low dose against placebo in the primary endpoint, I will pass the entire alpha I have, that is alpha half in this case, to the next node. That is the primary endpoint of the low dose against control. So if I'm lucky against, no, if I'm successful, I should say, against placebo, I can pass on and test against active control. Same over here on the high dose, okay? Separately, same principle. And now if I'm successful against the active control, then I can split my alpha and I put half in this branch, which tests my secondary endpoints against placebo, and the other half in this branch, which goes on the same way against control. And I realize Chris is signaling that I'm running out of time. So let me move on. I think it's clear how I split my alpha here. Now the pandemic strikes and my trials are curtailed. Recruitment is stopped at 85% of the sample size. The placebo comparisons, they remain sufficiently powered, but I have a problem for the active control comparisons. So what am I going to do now? As you can imagine, I will try pooling as my approach. And I need to explain this. Let's focus on the left side. This is my first study. On the right side is my second study. And I'll come to the middle. You'll see in each study, let's say study 1, I test the low dose versus placebo, endpoint 1, 2, 3, 4, 5, and the same separately for the high dose. Identical approach for the study 2, but the point now is that the active control comparisons, they are performed on the pool of both studies. That's the idea. I make this a little smaller, and I will say that there's an additional requirement here, and that is any endpoint can only be tested versus active control in the pool if it shows superiority in each of the separate studies versus placebo. This is an additional requirement. I can only work in the middle if the corresponding endpoint is significant in both studies against placebo. And that is, in some sense, a statistical poolability check. One question is, well, how do I set the type 1 error rate in this middle part here in the pooled analysis? And you can see here, without going into details, that I have to subtract some portion from the alpha I have. And by doing that, I control the type 1 error at 0.025 at the study level for oral placebo comparisons and 0.025 at the submission level for all hypotheses, including those against active control. Just quickly a graph here. You can see on the left side placebo, right side active control. I compare the power at the program level with, between the individual strategy in red and this pooling strategy in blue. And you can see, especially on the right-hand panel, active control comparisons, especially the secondary endpoints, they have a massive power gain, obviously, by the pooling strategy. Finally, discussion on the case study, and that's my slide before the last, Chris. The case study is not just a numbers game. A replication is a very important notion, so it's not just about power overall. The notion of replication can still be provided by separate analysis by study, which provides some kind of consistency estimate, even though it is after the official hierarchy. Of course, we need to specify things a priori. We need to be transparent also to authorities. And I just want to quickly say that there's much more to the story. I haven't covered here: logistics, estimates, sensitivity analysis, etc. And the story even continues because recruitment has restarted such that actually the trials could be completed. However, we cannot exclude that there's heterogeneity between those patients recruited pre versus during the pandemic. So the final proposal, which I haven't discussed here, is something in the middle. It is using some pooling approach, but not exactly the one I've presented here. The one I've presented here is more kind of prototypical, where everything against active control is based on the pool. Final conclusions. Leveraging external data, I believe, may help mitigate the impact of force majeure trial disruptions. We can consider various types of data sources. there are a number of quantitative approaches at our disposal. I have mentioned a few of them, and maybe this audience knows more. We have to be aware of a number of different caveats, which I've mentioned in one of the slides before. But still, perhaps extraordinary circumstances require extraordinary measures, while still providing substantial evidence of effectiveness. And of course, one thing I haven't touched upon is that we need sufficient safety information. And with that, I hope I'm not too much over time. Thank you.
Thank you, Mark. That's great. And do we have any questions? Again, saying this is to clarify, because we got plenty of time to discuss in the workshop sessions later. Any questions for now? If not, and I think that was very clear, so thank you, Mark, getting through a pretty complicated scenario. We'll have our short break now, and we've overrun a little, so I think we just make this a 5-minute break. So get a, well, not a breath of fresh air, it's not time for that, but whatever you can do in 5 minutes. And we'll start again at 25 past with our third speaker. Thank you. We're on to the third talk, and so we're very pleased to have Heng Li, who is a mathematical statistician and a leader at the Center for Devices and Radiological Health at the FDA, where he has been since 2002 and working in the area of cardiovascular medical devices. And well, we have Heng's title here. So leveraging external data via propensity score integrated approach. Over to you.
Thank you. Well, first, I would like to thank the organizers for their invitation. In today's talk, I will describe how to salvage clinical studies stopped by an unforeseen event, such as the outbreak of the COVID-19 pandemic, using a set of recently developed statistical procedures called the propensity score integrated approach. These include Bayesian procedure and the frequentist procedure. In the Bayesian procedure, the propensity score methodology is used in conjunction with the technique of power prior. And in the frequentist procedure, propensity score is used in conjunction with composite likelihood. We'll go over both procedures in this presentation and how to apply this tool to borrow external data to augment a clinical study cut short by COVID-19. The study that's cut short will be henceforth referred to as the current study. The objective is to restore the study power as originally planned while maintaining study integrity. We will review the 3 statistical ingredients of our method, namely power prior, composite likelihood, and propensity score. But first, let me briefly summarize the basic ideas of the propensity score integrated approach to leveraging external data. What does leveraging mean, you may ask? Well, by the end of the talk, this should become clear. Here, let me just tell you what it doesn't mean. By leveraging, we don't mean simply pulling the external data and the current study data. It is almost always the case that we need to discount or downweight the information contributed by external data so that external data do not overwhelm the current study data. As used in this context, the 2 words discounting and downweighting have essentially the same meaning. In this presentation, I use one for the Bayesian procedure and the other for the frequentist procedure. For our methodology, discounting is achieved via power prior in the Bayesian procedure, and downweighting is achieved via composite likelihood in the frequentist procedure. At this point, one may ask, where does propensity score come in? Well, let me first provide a high-level answer to this question. Many people are familiar with the role that propensity score plays in conducting causal inference in observational studies. The key to the usefulness of propensity score in practice is its balancing property. In the case of causal inference, this property is used to balance subjects' pretreatment characteristics between the treated group and the control group to make the comparison less biased. In our methods, we also use the balancing property of propensity score. But the groups to be balanced are not treatment groups. They are the subjects in the current study as one group and the external subjects as the other group. Why balancing these two groups? Well, that's because leveraging external subjects is more justified if they look alike. If the external subjects look like the subjects in the current study. In more statistical terms, leveraging is more justified if the distribution of the covariates among external subjects is similar with the distribution among current study subjects. For example, if the external subjects are mostly old and current subjects are mostly young, it may be considered inappropriate to directly leverage the external subjects without addressing the issue of age imbalance. The statistical procedure to be described in this presentation do just that. They address the issue of covariate imbalance between external data and current study with the help of propensity score. Now let's review the ingredients of propensity score integrated approach one by one. First, power prior, then composite likelihood, and then propensity score. The power prior is originally intended to be an informative prior constructed from historical data. If we substitute external data for historical data, then it fits our purpose perfectly. A power prior pi for a parameter theta based on external data d0 is shown on this slide. In this expression, L theta d0 is the likelihood function of theta given the external data. Pi 0 theta is the initial prior distribution for theta. And the exponent alpha is called the power parameter. It is between 0 and 1. From this construction, alpha can evidently be interpreted as the fraction of information external subjects contribute to the inference for theta. For example, if alpha is 0.1, each external subject contributes 10% of their information. The total number of external subjects multiplied by alpha is often interpreted as the nominal number of subjects being leveraged from the external source. If alpha equal to 1, then the number of subjects leveraged is equal to the number of all the external subjects. At the other extreme, if alpha equal to 0, then no subjects are leveraged. Clearly, to use this procedure, the value of alpha needs to be determined. As we will soon learn, the determination of alpha is not that painful in our methodology. And it is done at the study design stage, as it should be, in order to maintain study integrity. So much for power prior. Now let's turn to composite likelihood. The composite likelihood for a parameter theta is a weighted product of probability density functions, where each I represents a subject, and the lambda I is the non-negative weight. Clearly, when all the lambda i's equal to 1, composite likelihood reduces to ordinary likelihood. To use composite likelihood to serve our purpose of downweighting external data, we let lambda I equal to 1 for subjects for the current study, and lambda I between 0 and 1 for subjects from the external data source. For example, if lambda I equal to 0.6 for all external subjects, then each external subject contributes roughly 60% of their information. And the nominal number of subjects leveraged is 60% of the total number of external subjects. The maximum composite likelihood estimator for theta is asymptotically normal with mean equal to theta and variance equal to the inverse of the information matrix. With this result, statistical inference for theta based on composite likelihood can be conducted in a similar manner to that based on ordinary likelihood. The question of how and when to specify the lambdas is answered in the same manner as that for the power parameter alpha. Now let's review the concept of propensity score. The propensity score methodology is a groundbreaking statistical innovation for the design and analysis of observational studies comparing two treatments, developed by Rosenbaum and Rubin in the 1980s. A subject's propensity score is defined as the conditional probability of going to treatment group A rather than treatment group B, given a collection of baseline covariates. As an immediate consequence of the definition, propensity score is a balancing score. In other words, among subjects with the same value of propensity score, the distribution of covariates in the treatment group A is the same as that in treatment group B. In other words, among subjects with the same value of propensity score, the two treatment groups are balanced with respect to baseline covariates. So propensity score can be considered as a means for dimension reduction. It reduces the task of balancing many covariates, which is very difficult, to that of balancing one variable, which is relatively easy. In an observational study, the goal of balancing covariates is to make the comparison between treatment groups less biased. In our application, the goal is to simultaneously balance many observed covariates between the external subjects as one group and current study subjects as the other group, to make leveraging external subjects more justified. Propensity scores are usually not known in an observational study. They need to be estimated via logistic regression or some other method. Estimated propensity scores can be used in several ways. They can be used for matching, stratification, or weighting. In our application, propensity score stratification is used. A very important feature of propensity score methodology is that it can separate study design and outcome analysis. To explain what this means, let's consider traditional way to adjust for covariate imbalance in observational studies by regressing outcome on covariates and treatment group as a dummy variable. When selecting the regression model, bias can creep in because the analyst may favor models that lead to the conclusion that supports the study hypothesis. Since propensity score modeling does not involve the outcome variable can be kept out of sight from the analyst. When the analyst is blinded to the outcome, bias in model selection can be avoided. Therefore, in regulatory settings, we recommend that an independent statistician perform the estimation of propensity scores and the subsequent matching and or weighting or stratification. Having gone over the preliminaries, let me present the propensity score integrated approach and its application to salvaging clinical studies cut short by an unforeseen event, such as COVID-19. In this slide and the following ones, PS is an abbreviation of propensity score. PP is an abbreviation of power prior, and CL is an abbreviation of composite likelihood, and RCT is an abbreviation of randomized controlled trial. The PS integrated approach is relatively new. It can be used to augment a single-arm study or one or both arms of RCT. The best way to describe this approach is via an illustrative example. For simplicity, we will use a single-arm study as our illustrative example. Once we understand how this approach is applied to a single-arm study, the generalization to RCT is straightforward. One way to do it is to treat each arm of the RCT as a single-arm study and proceed accordingly. In the PS integrated approach, propensity score is used for study design, and either power prior or composite likelihood is used for outcome analysis. At this point, you may ask, what do you mean by study design when most of the subjects have already been enrolled into the current study? Well, this talk is based on the premise that although the current study has been stopped, the outcome data hasn't been unblinded. So the leveraging of external subjects to augment the current study can be viewed as study design modification and is therefore still part of the design. Remember that in our application, propensity score is used to balance covariates between the current study subjects as one group and external subjects as the other. So propensity score is defined accordingly as the conditional probability of a subject being from the current study instead of the external source. The modification of the study design consists of propensity score estimation and the following three activities, all based on estimated propensity score. Number one, select subjects from the external source that are comparable to the current study subjects. Number two, stratify the selected external subjects together with the current study subjects. And number three, specify the power parameter alpha in the Bayesian procedure and the exponent lambda in the frequentist procedure. The propensity score estimation plus all three activities are done without looking at the outcome data. Altogether, they constitute the modified design, which is outcome-free, as it should be. Before getting to the illustrative example, I need to mention several very important caveats. Number one, it is critical to assess whether leveraging external data fits for purpose for the specific objectives of the current study. Number two, it is critical for the external data source to be relevant and reliable for regulatory decision-making. In other words, it is essential to make sure that external data source to be used is of high quality and has integrity. Number three, outcome-free design is an imperative. Number four, early consultation with relevant FDA review division is important, and so is checking out available FDA guidance documents. With the above points in mind, the propensity score integrated approach can be used to augment the current study with external data, where the current study may be a single-arm study or an RCT. Now, after all the preliminaries and caveats, here is the illustrative example for the propensity score integrated approach. As I just mentioned, this method can be used for either a single-arm study or an RCT. We use a single-arm study for an example for simplicity. Consider a single-arm clinical study for medical device. with the primary endpoint being 1-year adverse event rate. The parameter of interest, theta, is the probability of a subject experiencing one or more adverse events within first year. The null hypothesis is theta greater than or equal to 36%, and the alternative hypothesis is that it's smaller than 36%. In the original sample size calculation, theta is assumed to be 30% to achieve 80% power at a significance level of 0.05. 380 subjects are needed. Then the pandemic broke out and the study had to stop enrollment at 290 subjects. It is not practical to reopen the enrollment again. As it turned out, the investigational device has been on the market in Europe, and there was a registry there that captured the primary endpoint and thus can serve as a source of external data. A proposal was then made to modify the original study protocol to borrow 90 subjects from the external source to complete the study. The proposal included the identification of an independent statistician blinded to the outcome data who was to perform the activities specified in the modified plan. The independent statistician would play a critical role in maintaining the study integrity, as we will see. This proposal got the green light from FDA. The European registry was then contacted, and 941 subjects satisfying the inclusion-exclusion criteria were provided with all the covariate data. These were the subjects who could potentially be used to augment the current study. The covariate data of the 290 subjects from the current study and the 941 subjects from the registry were then sent to the independent statistician, who was asked to build a propensity score model between the current study subjects and registry subjects in order to balance all the covariates between these two groups via stratification. To ensure the integrity of the procedure, it is important not to look at the outcome data when building propensity score model to balance covariates. That is why an independent statistician blinded to outcome data was appointed. As requested, the independent statistician performed the propensity score stratification. They used a logistic regression to estimate propensity scores and divided all the subjects, including the registry subjects and the current study subjects, into 5 strata. They used propensity score quintiles among the current study subjects as strata boundaries, so that there are equal number of current study subjects in each stratum. They checked balance within each stratum for each covariate and sent the balance assessment to the sponsor and the FDA. It was satisfactory. Now that the independent statistician had the data set containing all the subjects' propensity score strata membership, the rest of the data leveraging process began. But before describing what the independent statistician did next, let me revisit the purpose of propensity score stratification. The purpose is to create sets of subjects within which current study subjects are similar with registry subjects, so that data leveraging within these sets are more justified. As has been mentioned earlier in this talk, data leveraging is to be carried out with power prior for Bayesian or composite likelihood for frequencies. So the remaining problem is how to determine the power parameter alpha or the exponent lambda. We do this by first determining how many subjects to leverage within each stratum. Recall that the total number of subjects to be leveraged is the planned enrollment minus the actual enrollment, which is 90. Since leveraging takes place within strata, we need to figure out how to allocate the 90 subjects to be leveraged to each stratum. A simple way is to divide them evenly so that each stratum gets 18. But we can also do it in such a way that favors strata in which the two groups of subjects are more similar in terms of covariates. In other words, we leverage more in strata with less residual imbalance. To implement this idea, we first choose a numerical measure of similarity. One option is to choose overlapping area between propensity score distributions as a measure of similarity. And then we can let the number of subjects to be leveraged in each stratum to be proportional to this overlapping coefficient. This table shows the overlapping coefficient in each stratum. For example, in the first stratum, the overlapping coefficient is 0.87. In the second stratum, it is 0.78, and so on. Then we calculate the standardized overlapping coefficient for each stratum, which is overlapping coefficient divided by the sum of all overlapping coefficients. For example, in the first stratum, the standardized overlapping coefficient is 21%. And in the second stratum, it is 19%, and so on. Then we multiply the total number of subjects to be leveraged, which is 90, by the standardized overlapping coefficients. In the first stratum, this is 21% times 90, which is 19. That means in the first stratum, we are going to leverage 19 subjects, and so on. As we can see, in this specific case, the allocation of the 90 subjects to be leveraged is almost the same as even split. Having allocated the 90 subjects to be leveraged to the 5 strata, we can determine the power parameter alpha, or the exponent in the composite likelihood function, lambda. All we need to do is to divide the number of registry subjects by the number of subjects to be leveraged in each stratum. Therefore, in the first stratum, the alpha or lambda is 0.07, and so on. Now we know the propensity score stratum each subject belongs to, the amount of information each subject contributes in each stratum, we can simulate study operating characteristics. As it turns out, the power happened to be 80% and type 1 error is 0.05. At this point, the study design was complete. The independent statistician's job is done, and we were ready for outcome analysis. For the power prior approach, once we know alpha for each stratum, we know the prior distribution for theta in each stratum. So stratum-specific posterior distributions for theta can be found. These posterior distributions are combined to complete the inference for theta. As it turned out, the posterior probability of the alternative hypothesis is 96.9%. The primary endpoint is considered as being met. For the composite likelihood approach, once lambda is known for each subject, maximum likelihood estimate can be found for each stratum. They are then combined to complete the inference. As it turned out, the p-value is 0.1, which meets the primary endpoint at the significance level of 0.05. In conclusion, novel statistical methods play a critical role in leveraging external data to support regulatory decisions. Propensity score integrated approaches can be applied to incorporate external data for prospective investigational clinical studies. Propensity score integrated approach can be utilized to mitigate study power loss due to the COVID-19 pandemic. There are some guidances, here are some references, and thanks for your attention.
Thank you very much, Heng. So once again, can I ask, are there any short questions to do with understanding? Again, I think that was remarkably clear given the complexity of some of the topics there. So could